Hello and welcome back to Calculus2. A little bit of technical difficulties until I had to reconfigure my internet because I was playing with things. Never shortage of fun with tech, right? So now we are going to finish chapter 11, which will get you ready for we will get you ready to work with power series, right? And then exam is this weekend. We are going to also have the topics review and so on for this exam. And then if you guys are interested, we can have office hours and then another review and lecture on Thursday to wrap things up with the course. All right, so let's talk about power series. We already talked about the fact that power series are supposed to approximate the functions, and we saw that the more terms you have, the better approximation it is, and we see that if there is infinitely many terms involved, then the function is equal to the power series. So f of x is equal to summation of cn x to the n from 0 to infinity, or f of x is equal to summation 0 to infinity cn x minus a to the n if it's centered at a. So if you're looking for the values that are not at 0 or around 0 but a little bit further away. And 1 is already infinitely far away, so that's another thing that you have to be careful. So the first order of business is to look at the what we would call radius and interval of convergence of power series, because power series are supposed to converge. Let's see first. So let's go and see what it means for a power series to converge, to have this interval of convergence or a radius of convergence. They pretty much show the same thing. So we're going to consider three examples. We're going to consider three examples, and we are going to understand this radius of convergence. So I'm going to start with example that it's not given in the book, and then we'll take the three examples that are really good examples in the book. But let me start with the example that it's not in the book, and that's going to be x divided by 4 to the n from 0 to infinity, right? So this is an example that, could be a standard example or so on. But what is happening here? Let me actually move this down and put a title, because we are going to do a couple of different concepts here. So now we're talking about interval and radius. Interval and radius of convergence. All right. Now, what I want to first just consider this a little bit to understand why we are bothering with this thing of convergence and so on in the first place. Pick x to be 2. If you pick x to be 2, the power series converts to a regular series of 1/2 to the n, and that's geometric series, and that converges. Pick x to be 10 or 20, whatever, 20, so it becomes sum of 5 to the n, which diverges. You see that? So for power series, convergence or divergence of the power series, in the sense of chapter 10, right, depends on your choice of x. So there are going to be x's, many or one or few, whatever, for which the problem is going to converge, and then there are those choices for x that will make it diverge, right? So we have to be careful, and we would like to calculate the interval of convergence, meaning we want to find the, let's say, 2x values, right, that will have all of the x values for which the power series would converge, and then outside of that interval of convergence are obviously all x's that would make it diverge. So see over here, obviously x equals to 2 is inside the interval of convergence because it converges when x is 2, but 20 is outside of it, right? So we would like to find exactly what the numbers are, and to find that you will be using ratio test from chapter 10, right? So the way we do this, I'll put this in blood. Use ratio test. There are a few options. You know, sometimes you can also use a root test. You can use a root test now as well. But ratio test is standard, and I would say 99% of the problems will be ratio test, and then sometimes root test creeps in. You can use root test right now, but let's use ratio test. So what is my AN, right? My AN for ratio test is x over 4 raised to the n, and the AN plus 1 is x over 4 to the n plus 1, right? Now we know that for the ratio test you are supposed to divide these as n goes to infinity, and you are supposed to divide them inside absolute values. Now, if you don't have absolute values when you are dealing with these with the ratio test here, you are going to have wrong answers. You are going to have problems. It will not be good. So you must have absolute values. So this is x over 4 to the n plus 1 divided by x over 4 to the n, and then you just need to solve this limit. So now we're going to have x over 4 times x over 4 to the n times 4 over x to the n in absolute values. The bottom one goes as a multiplication, right? And it flips. That's the way you divide by a fraction. So that's basic algebra. Limit n goes to infinity. And now you see that these guys completely cancel, right? X to the n will cancel with x to the n in denominator. 4 to the n and 4 to the n cancel. So they all cancel, and what you are left with is x over 4, and it's important for it to be in these absolute values. Now, I'll write this in blood, less than 1, because we want convergence. Okay, so what is the goal of the problem? The goal of the problem is to find x's for which power series converges. So, because we want the convergence, we are the ones that are setting this less than 1, because that's what we want, right? So, doing this, right, is something that we want, because we want the convergence. And now we have to solve this. Now observe that this has no n, so limit will do nothing to it. So we'll just have x over 4 in absolute values less than 1. Now, if you studied algebra carefully, you know that this is going to be negative 1 less than x over 4 less than 1. That's how you get rid of the absolute values. And then multiply the whole equation by 4 to get x alone. So you get negative 4 less than x less than 4. This is known as the interval of convergence. That's it. Interval of convergence is negative 4 to 4. Any number that you pick between a negative 4 and 4, you cannot pick negative 4 and 4, but any number in between them Negative 3.9875 is fine, 0 is fine, 2 is fine, negative 2 is fine, pi is fine, e is fine, 1 over e is fine, right? All of the numbers that are between negative 4 and 4, anything you pick for x, you will get the power series to transform into a geometric series which converges because you picked the x from this interval. If you pick 4 or more, or negative 4 or less, you will convert your power series into a divergent a divergent geometric series. So power series is a power series because it has x in it. As soon as you assign a value to x, it becomes a regular series from chapter 10. And in this case, in this particular problem, it becomes a geometric series, right? Because that's the shape. That's the shape of it. Now, radius of convergence over here is 4. Because if you on the number line, right, if you graph your negative 4, right, you see that the radius of convergence is just on one side, right, half. This is your x, actually, axis, right, the number line. And we're done, right? That's the radius of convergence. Radius of convergence is half of your integral of convergence. One more thing I want you to pay attention now, but we'll see that later. Observe that your center, right, from which the radius is emerging, is at 0. And observe your power series, it's x minus 0, centered at 0. That better match. The center of your interval, the midpoint of your interval, and the a value for this problem, they better match every single time. All right, now we are going to discuss the 3 examples that are given in the book. They're amazing because they clearly show all 3 cases, right? The example I did is actually the middle example from the book, but they have a little bit different examples, so we'll deal with that as well. All right, so should I say type 1? Maybe type 1. I don't know. Summation of 0 to infinity x to the n over n factorial. Right? Immediately get your an, which is x to the n over n factorial. Immediately get your an plus 1, which is x to the n plus 1 over n plus 1 factorial. And limit n goes to infinity of x to the n plus 1 over n plus 1 factorial, and I'm immediately going to flip the other one and write it as a multiplication, skipping a step. Now we're going to do the limit n goes to infinity, peel off an x, peel off n plus 1. So standard ratio witchcraft, we are not learning anything new, right? It's nothing new. We're canceling what we can, and we are left with the limit n goes to infinity of x over n plus 1. Now, in this case, we can drop absolute value. Well, you can kick x outside with absolute values, right? And limit 1 over n plus 1, no need for absolute values because n is all positive numbers anyway. What you get is absolute x times 0, which actually equals to 0, and that is always less than 1. So, conclusion is that this power series is always convergent. Always. So what is the interval? It's convergent for all x. So negative infinity to positive infinity. And what's the radius? Radius is infinite. So this particular power series is convergent for every value of x that we have for our power series. Any value of x that you can come up with, it's definitely convergent. The next one, call it type B, type 2 actually, type 2, is the one that we already did. It is going to have some interval from a number to a number, right? So it's not infinite. So this one, even though we did already example, let's do another one. Negative 1 to the n, x minus 2 to the n over 4 to the n. They have k's, whatever, we do n's. Anyway, so what is my an? My an is, we're not going to worry about negative 1 term because we don't have to, right? The absolute value is going to kill it. So ignore it. So all of these guys now are going to be increased by 1 for an plus 1. We immediately go and do the ratio test. And absolute value. And you can, if you are visually, divide this by that, right? You can start peeling immediately. X minus 2 to the n divided by 4 times 4 to the n times the flip, because it was divided, so you have to get that one. And now that's that, and what you get is limit n goes to infinity of x minus 2 divided by 4. Well, as I said earlier, there is no n. There are no n's over here at all. That means that this limit has nothing to operate on. Therefore, we can just drop that limit and get our x minus 2 over 4. And then we are the ones who set this less than 1 because we want convergence. Now, if you studied algebra carefully, you know that you are supposed to say negative 1 less than x minus 2 over 4 less than 1. You multiply everything by 4 to kill that denominator there, so you get negative 4 less than x minus 2 less than 4, right? Because it's a three-sided inequality, you have to multiply each one of these by 4. And now you add 2 to all three sides, and that gives you negative 2 less than x less than 6. So the interval is negative 2 to 6. Make sure you are using parentheses because the endpoints are not included in this interval. So 6 will make it diverge, right? 6 will make it diverge because it will give you the r equals to 1. And r equals to 1 is divergent on the geometric series test. Now, what is my radius of convergence? Well, what is the length of this interval from negative 2 to 6? It's 8 units, right? So interval is 8 units long, so radius is 4. That should be common sense. It's half of the whole interval, right? Now, if I graph this, it better line up with our center that and blah, 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 right? We learned earlier. Let's graph it. So I have my negative 2. Then there's my 0, 1, 2, 3, 4, 5. Here's my 6. All right? That's my x-axis. What have I learned? I learned that I have 4, radius of 4, right? Because I have 8 units. So radius of 4 has to emerge from 2. Going this way, radius is 4. and going this way, radius is 4. Where is that center? X equals 2, right? Now, go back to the start of the problem. Where was your power series centered? It was centered at 2, A equals 2, right? Remember that we said that when its power series is centered, it's centered at x minus a, right? X minus a. You have x minus 2. Therefore, a is 2. Center is at 2 in our case. All of that has to click in. You have multiple points to check your problem, right? Really no excuses for getting this stuff wrong if you studied. So the type 1 gives you infinities. Type 2 gives you the this interval that has numbers in it rather than infinities. And now we have the type 3. That's our example C. Great example. 1 to infinity of n factorial x to the n. This one should be easy. I'm going to give you 20 seconds over here to solve this one on your own, right? Because it's just a joke. You don't even have a double fraction on this one. It's just, you know, you don't even have the double fraction on this one. And obviously, if you have any questions, just type them in the chat. All right, so the time is up long time ago, right? Limit n goes to infinity of n plus 1 times n factorial times xn plus 1, right? When you peel off, oops, no plus 1 anymore. When you peel off plus 1s, and then the bottom is just n factorial x to the n, right? So now when you cancel these guys, you run into limit n goes to infinity of absolute value n plus 1 times x. Right? Now, if you kick the absolute value x outside because limit doesn't apply to it, you have limit of n plus 1 as n goes to infinity. That's going to give you infinity, right? So, what is the only way for this to converge now? Is there any, because you can't say, you know, if this is going to be infinity, then this is 1 over infinity, and then infinity is cancelled. None of that nonsense works, right? There is only one thing that can save the day. If x equals to 0, then we have convergence. So, there is no interval of convergence. It converges at a single point. So, converge at a single point x equals 0, and radius is also 0. So that's the type. That's a type 3. And now you have seen the way to determine the radius and interval of convergence. There is a summary of this procedure, right? All 3 points explained in the summary on page 725. Just quickly look at that if you're interested, right, for the more. But the exact 3 problems that are done plus that extra introductory one, right, examples are all here in this lecture. Now we have few more theorems here that will help you combine power series, what we say, make new power series from old, right? Combining power series, because remember, power series essentially represent functions, and you can add functions, you can divide functions, you can multiply functions, you can square functions, and you can do function composition, right? So combining power series. So let f of x be the power series Cn x to the n from 0 to infinity, and g of x, right, let they converge to those functions, to have dn x to the n, right, 0 to. Now if you want to have a minus, you can. First rule is that if you have a power series which has ck plus or minus, well, dn, sorry, use n's, and the book is using k's, and it's just a whole mess. There we go. So this is the same as if you actually had these two split up, each one of them having their own summation. So you can combine them into one, as long as they are starting with the same value, as long as their x to the n has the same power. So you have to do that shifting and dancing around. And that converges to f plus or minus g. So that's the standard sum and, right. Then also, now guys, what I'm writing now in blue, you are going to need for differential equations chapter 8 when you do the power series solution to the differential equations. If you don't know this stuff in blue, there will be no chapter 8 for you in DFQs. You absolutely must know everything that I'm writing right now to have a chance of solving those problems. There's no guarantee you're going to solve them, but just to have a chance, right, you got to know these. The next one is multiplication by a power. If you have some x to the m multiplied into Cn x to the n power series, then this can go in, and you'll have your n plus m, which is just a standard algebra, right? Now think about this. This is going to have infinitely many terms, and then each term, right, will distribute this one. Well, then just they will all add to this one anyway. Doesn't matter, right? And here's the biggie. This is the one that we are also going to use in 10 minutes. And also people in differential equation. It's function composition, which means that you can import the entire function inside the power series. And obviously this one is the one that requires a little bit more work. So if h of x is given as bx to the m, oh, I see the differential equations crew is in, brushing up, right, for the reckoning for tomorrow, 8.2. Nice. Glad to see you guys. All right, so yeah, DFQ students are watching this stream because they gotta use all of this stuff tomorrow to solve differential equation. All right, so if we have some kind of a function here, it's a polynomial, clearly. For positive integer m and non-zero b, right? If b is 0, then this whole thing is 0, so it's pointless, right? Then, oh no, and we have a power series, just a regular Cn x to the n, which converges to f of x. Then, I'm rewriting it a little bit cleaner than what the book has. Then, power series of Cn age of x to the n, right, is the function composition, which means that you can have summation Cn be x to the m to the n from 0 to infinity, and that is f of x of age. Function composition. Now, this one immediately requires an example, right? The ones on the top are 1 and 2, they're nothing special, but this one over here is going to help you. We learned already that e to the x is 1 plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24 plus ... Right? Okay. Do we need e to the x to do some heavy-duty calculus? Do we need power series for e to the x? Hell no! No! Derivative of e to the x is e to the x. Integral of e to the x is e to the x. Easy to find domain, the range, shifted left, right. There is no need for power series, right? If you need to integrate, we have, right, x times e to the x. We can use integration by parts, right? So we are all set. E to the x, beautiful function, right? The best function for calculus. But the last part of today's lecture is integrate e to the x squared dx. Ooh, right? We open the gates of hell right there. There is nothing that you can do with this one. I mean, there are techniques, Calc3 and so on, but, right? None of the things you learned work. You can't do u sub because you don't have x in front. You can't do integration by parts because you don't have, again, x in front, right? So it's not a polynomial to do partial fraction decomposition. You can't do the trigonometric substitution. There's just literally, just cry, all right, when you see this. However, if I am able to write this as a polynomial some way, all of a sudden, the integration would be a joke, wouldn't it? So now from here, what is e to the x squared rather than e to the x? Well, by this theorem here, all I need to do is to go here and replace every x I see with x squared. And we're good to go. So what do I get? I get 1 plus x squared plus cubed over 6 plus the 4th over 24 plus ... and each one of these parentheses is x squared, x squared, x squared. If this over here was tangent x, then there will be a tangent x in each one of these replacing, because it's just a simple function composition. Now, work out your algebra. 1 plus x squared plus x to the 4 over 2 plus x to the 6 over 6 plus x to the 8 over 24 plus ... forever. How many terms do you need to keep? Depends on the precision you need. We talked about it. 3 or 4 terms, right? When you want to experience a little bit more pain than usual, you will use 4 terms. Generally, 3 terms are okay. We saw how well sine function follows, power series follows sine function with 3 terms, right? It went all the way beyond the first quadrant, almost reached pi. That's insane precision, right? For only 3 terms. So my integral of e to the x squared dx is about as good as integral of 1 plus x squared plus 1/2 x to the 4 dx. Jumping from something you can't do at all to this joke, these power series are insanely useful. Insanely useful. Now some of you might say, well, does this technically zero out everything we ever learned? Can we just use this for every example? The answer is, if you are able to obtain the exact answer, why would you use the approximate one? Remember, in order for this to be exact answer, I need all infinity of these terms that I just threw into garbage. Actually, from here. You see that from here all the way out? I threw all of that to garbage and I use only first three terms. Clearly the stuff that I throw away is going to create error. So if I have a problem that it's a U sub, or problem that is a trig sub, right, it's still better to do it using those techniques, right? But for these kind of situations, yeah, power series is going to be... So think of a power series as this enormous sledgehammer, like Thor's hammer, right? Only Thor can lift it, right? In special situations, if he's worthy, right? So you get to use this power series sledgehammer on the integral problems, right? Do you ever have to use it for differentiation? No! You can differentiate anything, but you cannot integrate anything, right? There are certain problems that are not integrable, and then we have to resolve to the sledgehammer approach over here. Now, we still learn differentiation with power series because differentiation with power series will be used in differential equations to solve differential equations. So we still need to know how to differentiate with power series, right? If I want to take the derivative of sine x, we all remember, oh yeah, derivative of sine is cosine. Why? My professor said so. Okay, let me turn into a 5-year-old. Why? My professor said so. Why? Because I'm not happy with the answer your professor said so or the book said so. Why is the derivative of sine equal to cosine? Right? The other question is also, right, well, you can use that really long definition with the, x plus a, f of x plus h minus f of x divided by h, right? The limit h goes to 0 and all of that stuff that we learned, and eventually, you'll get it. Yeah, sure. We can do all of that. Or we can just make this into a joke using power series, right? The derivative of the power series, which was summation 0 to infinity, and what do we remember? It's the odd function, so all of the exponents are odd exponents, and the odd factorial over here. So that gives me what? It gives me x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. And you're saying, are we memorizing these? Well, if you are smart, you are going to memorize it now, so it's not killing you in differential equations. But you can also, cheat now and then get slain later. It's your pick your poison. Oh, I forgot the derivative in front. There we go. Woohoo! So now, what do? Well, just take the derivative of the polynomial, right? The derivative of x is 1 minus 3x squared, and this is 3 times 2 factorial, plus 5x to the 4th divided by 5 times 4 factorial. Right? Remember that the way I'm writing these denominators, I'm only peeling off 1, because I know they will cancel. What is 5 factorial? It's 1 times 2 times 3 times 4 times 5. Well, these puppies are 4 factorial, and then there is that 5 at the end. to make it into a 5 factorial. When I say peel off 1, that's exactly what I'm talking about. You peel off just the last multiplication, and then everything before that is the previous factorial. So minus 7x to the 6, peel off a 7, and you have 6 factorial left. So it's just the standard stuff. Yeah, you'll see it in differential equations. Plus 9x to the 8 over 9 times 8 factorial minus dot dot dot. What now? Just cancel all of these constants. There we go. And get what? 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial minus dot dot dot, which condenses into negative 1 to the n. All of the powers are even. Factorials are all even. And that, my friends, is the big old cosine x. Derivative of the sine is cosine. Go ahead, do the integration. Do the integration. Derivative of, integral of sine is negative cosine, and integral of cosine is sine. You will, if you integrate term by term, it will give you exactly what you need to have. Right? It all has to link in and click in. What else have you learned about, I mentioned this last class. Your professor said something else when you took pre-calc 2. Said, sine is the odd function. Yeah, we know that now because all of the powers are odd. That's the odd function. Cosine is even, sure. I know, right? Power series. Next time you tutor someone, trig, and they come up with the even and odd functions. Yeah, there you go. You can show this to them. The expansion for sine and cosine. There's a reason why they're even and odd. It's not arbitrary, right? So you have something to memorize. It's clearly what it must be. What else do we? Simple problem. The derivative of e to the x is e to the x. Is it? Yeah. You can just look at it. It should be immediately obvious that you are getting the same thing back. Derivative of 1 is 0, plus derivative of x is 1, plus 2x over 2 times 1 factorial, plus 3x squared over 3 times 2 factorial, plus 4x cubed over 4 times 3 factorial, plus, what do we get? 1 plus x over 1 factorial is just x, plus 3's cancelled, 2's cancelled, 4's cancelled, x squared over 2 factorial plus x cubed over 3 factorial plus, that's e to the x. These power series are insane. I love them. Now, it's a lot of mess, right, when you start dealing with these things in differential equations. I did this last night. It was a lot of fun. But there's a differential equation. There's your power series. There's the derivative of the power series. You are expecting to see that the derivative of x to the n is n x to the n minus 1. That's your calculus 1 formula. Then you plug in this one there, this one there, and then you have to go and compute all of this mess that we did, right? And more stuff coming tomorrow. Guys, you are going to use this stuff. This is not something arbitrary so you can take your exam and pass Calc 2 and be done. These things are going to be used. Are you going to take thermodynamics? You're going to take some advanced chemistry, some advanced physics. Are you going to take advanced math courses? You're going to take partial differential equation. Well, more than half of each one of that course, electrical engineering or anytime with signals and stuff, more than half of every single one of those courses will have this as calculations, just basic calculations for the problems, homework, exams, everything. You have to know this is elementary mathematics. It's very powerful, right? But you need to sit down. You need to figure these things out. It is used. Once you have a complicated function, whether it's composite or non-composite, you will break it into this type of a polynomial. As you can see, keep 3-4 terms and then do the derivative of each of the term, do the integral of each of the term, do the limit of each of the term, right? There is nothing special there. You will simply just go through the all of these calculations term by term. So calc with power series is done term by term. That's it. So what have I done? I have some kind of a function, whether it's a basic or composite. The first order of business is to write it as a polynomial, and from this step to this step is where I actually did calculus when I differentiated. But I was differentiating a polynomial. So that's what the power series do for us. They make a joke out of terrible situations. And yes, they could be messy and long to write out and so on. But in essence, come on, when you're stuck without any options, all right, power series save the day. Now, the last thing for this, and then we'll restart the stream for the exam review, is to talk a little bit about this business of centering power series so you can solve integrals and so on. A very important notion here. Say that you are calculating some residue energy or a difference in energy or a jump in energy, but they are slight jumps. Energy is area under the curve, so you are using definite integral. And let's say you are going to have, 3 to 3.2, and then integral of some, function over here, f of x dx, and f of x is not easy to integrate. You have to use power series. So f of x is evil, and we must use power series. All right, so you have to make sure that you are doing this correctly. If you just go in and do the power series centered at 0, which is Maclaurin series, for this problem, you are going to get a garbage answer. You have to be very careful about that, right? So f of x equals power series cn x to the n from 0 to infinity. No. You must use f of x equals summation 0 to infinity cn x minus 3 to the n because of your limits. That is something that you have to be very careful about when you start computing these things. This one is centered at 0, and that's no bueno now. 0 is infinitely far away from 3, right? Remember what's happening with your approximations for sine and cosine, right? If you use, that's your sine, you use one approximation, it's cool. Then you use the other approximation, it's a little bit better. and then the next one better, and then the next one better, right? So every time you add more terms, it's better and better and better. Centered at 0, right? When I had a little bit of these terms, centered at 0 was the one that was okay, but when you centered it at 0, it was only good from, let's say, 0 to pi over 6. Alright? That's it. Any calculation that you do after 6, your y value here and your y value here are really far apart. So you cannot use, right, that far away. When I say far away, come on, this is your 3.14, right? So you see that you can't use just 0 and 3 or, arbitrarily pick these points. You must center your power series around the value that was given to you in the integration limits. Otherwise, all of this is going to give you numbers that have nothing to do with the actual answers. Again, more terms you have, the better precision you have, and it's never going to be exact unless you're approximating polynomial with Taylor series, which is dumb because you're going to get the same polynomial back, right? It's a polynomial expansion of a polynomial. What are you going to get, right? That's where I derived my business idea. If you want to make a lot of money, just go and sell powdered water. It's so someone might buy it. I mean, people are buying religion, so they can as well buy that, right? Think about it, right? You add a gallon of water to a powdered water, and you get the gallon of water. There you go, right? It's very, very simple. So that's the same like approximating polynomial with powers with a Taylor polynomial. I mean, all right, cool. I'm going to restart the stream for the part 1 of our exam review, and then the part 2 exam review, when you bring in your questions and so on, will be on Thursday. So today we're going to take a look at the list of topics. If you have any questions, I can solve them. Shoot them in the chat, and prepare as many questions as you can for Thursday. Thursday we're going to do chapter 12 for about, I would say, 2 hours at least, and then we'll have another hour of review for exam 3. Exam 3 starts, I think, on Thursday or something, and then your final exam for those who want to take it is going to start on Sunday, May 10th. Sunday, May 10th is in 5 days, so yeah. All right, restart.